We'll often find it sufficient to model budget constraints in two dimensions, with the good that we're really interested in graphed on the horizontal axis, and a composite good, dollars worth of other consumption, graphed on the vertical axis to capture all the other consumption. But it's worth noting that we can also illustrate graphs of budget constraints with three goods, as we will do in this graph. In addition to our pants and shirts axis, we can now also have a third axis that measures the number of socks. If we have $200 and the price of pants is $20 a pair, we can buy as many as 10 pants. If the price of shirts is $10, we can buy as many as 20 shirts. And if the price of socks is $5, we can buy as many as 40 socks. Thus, bundles A, B, and C on the three axes are affordable to us with our $200 budget if the prices of pants, shirts, and socks are $20, $10, and $5 respectively. If we connect bundles A and B, we get the budget constraint we previously derived in our other graphs. It's the budget constraint that tells us what bundles of pants and shirts are affordable to us with our $200 budget, given that pants cost $20 a pair and shirts cost $10 each. Our previous two-dimensional budget over pants and shirts is therefore a special case that holds the number of socks fixed at 0. Or we could say it's a slice of a three-dimensional budget where we're holding socks equal to 0. If we connect bundles B and C, on the other hand, we get the budget constraint over shirts and socks, assuming that we buy no pants. And if we connect bundles C and A, we get the budget constraint over socks and pants, assuming that we buy no shirts. The three budget constraints we've drawn in the three planes that are formed by the axes are therefore two-dimensional budget constraints that hold consumption of one of the three goods equal to 0. If we then fill in the plane that's formed by these three green lines, we get the budget constraint in three dimensions, the budget constraint that illustrates all combinations of pants, shirts, and socks that are affordable to me with a $200 budget given the prices of 20, 10, and 5 for pants, shirts, and socks. Bundle D, for instance, lies on this green sheet that we've drawn. Bundle D contains 5 pants, 5 shirts, and 10 socks. 5 pants cost $100 at $20 each, 5 shirts cost $50 at $10 each, and 10 socks cost $50 at $5 each. Thus my total spending at bundle D adds up to my entire $200 budget, putting me on the boundary of my budget set. My three-dimensional budget constraint is therefore the green surface that we shaded in between the three green lines that we initially drew in the planes formed by the axes on the graph. Bundles, like bundle D, that lie on this constraint are bundles of socks, shirts, and pants that fully exhaust my income, in other words, bundles that cost me $200. My budget set, of course, also contains all bundles that lie underneath this green sheet, but those bundles will cost less than $200. And there are lots of two-dimensional budget constraints that are contained within this three-dimensional budget. Hold any of the goods fixed and slice the three-dimensional budget constraint, and you get a two-dimensional budget constraint, assuming a certain consumption of the third good. Mathematically, it's then easy to extend the idea of a budget constraint and a budget set beyond three goods, but graphically that becomes increasingly difficult.